Hello, welcome to this lesson on the delta delta. We're going to be talking about a particular mathematical formula that is represented like this in shorthand form. It's also known as the delta delta, which is something we use in acid-base balance. And we're going to go through this a little bit slowly because it's a complicated formula, but I hope that after we're done, you'll not only know how to calculate the delta delta, but you'll understand some more nuances about how this formula can help you in understanding a patient's acid-base balance. So let's begin, and what we'll do is, instead of starting out with what the delta delta is in terms of a formula, let's go through this particular chemical equation on which the delta delta is based off of. And so this is the chemical reaction that's occurring in the bloodstream when a patient is acidotic, and even when a patient is in rest and normal conditions. This is what's going on. Okay, so where we want to focus on right now is here. Any proton will combine with the bicarbonate buffer system that's inherent to the bloodstream to produce carbonic acid, which then breaks down to CO2, which you exhale. And this is how the body normally rids itself of excess protons. You exhale those protons away in the form of CO2. The other way is, of course, using the urinary system and the renal system to eliminate these protons. And the way the delta delta works is kind of as follows. If you have any organic acid being produced, and let's call that organic acid HA, where the A could be lactate or beta hydroxybutyrate or salicylate, formate in the case of methanol toxicity, glycoxylic acid, if I've pronounced that correctly, in the form of ethylene glycol toxicity. So it doesn't matter, but it's any kind of acid that will dissociate into A minus plus H plus. And those protons then participate in this equilibrium reaction to eventually form CO2, which you exhale. Now, for every organic acid that's generated, you get about an equal or proportional amount of protons. In the case of this example, you have 1 mole of protons combining with 1 mole of the acid, or the anion. So you have a 1-to-1 distribution. And what the delta delta is trying to ascertain is whether you've taken out a proportional amount of bicarbonate such that all of the excess protons come simply from the acid, and that there's no other mechanism that's causing bicarbonate to be eliminated. So let's elaborate on that some more. We're looking at the delta delta. The formula is actually the change in the anion gap over the change in the bicarbonate. Now, what I had initially said was that there has to be a proportional decrease in bicarbonate for all the protons that are generated. And so if you measured the change in the proton concentration over the change in the bicarbonate concentration, you should get a number that's about 1, because for every bicarb that goes down, it's because there's an extra proton that was generated. The difference is almost always the same, and that's how you get the number 1. Except it's very hard to measure protons. You could use the pH, but as you know, the pH is the log of H plus, and this is not an easy mathematical equation to work with, because most physicians don't have a logarithmic calculator on them to calculate the proton concentration and then the change in the proton concentration. What you need is some measurement of the amount of protons that are being generated so that you can compare that to the amount of bicarb that's being quenched. If the amount of protons generated is equivalent to the amount of bicarb being quenched, you have a ratio that's going to equal 1, and that means you have a pure acidosis, a pure metabolic acidosis, pure anion gap metabolic acidosis. You can't use this equation because it's cumbersome and many physicians don't have a calculator, so we're going to rely on a surrogate, and that's the anion gap. So let's clear this screen and go into a little bit more detail about how this works. Let's bring back this formula. Okay, H2CO3, which then breaks down to CO2 plus H2O. In a patient who has an anion gap metabolic acidosis, in other words, a patient who is generating organic acids like lactate or beta hydroxybutyrate or poisoned with salicylates, they are going to have an excess amount of protons. And those protons, in a 1-to-1 fashion, will be quenched by bicarbonate. So the increase in protons, for every 1 increase in proton, you'll get 1 decrease in bicarbonate, and the ratio will then be 1. So the delta-delta is as follows: the change in the anion gap over the change in the bicarbonate. Well, the change in the bicarbonate is easy to figure out, and it's easy to understand. For every 1 proton that you make, you get a drop in your bicarbonate, and that's how this number changes. You just look at the bicarbonate before the acidotic conditions set in, and then you look at the bicarbonate afterwards, subtract the 2, and you have this number here. But let's look at this anion gap. How does this work? So let's expand on this some more, and let's say that the anion gap is equal to the unmeasured anions minus the unmeasured cations. Now we know how to calculate the anion gap. We know that you look at the serum sodium and you subtract it from the chloride and the bicarbonate sum, and you get a number. But in reality, what you're really looking at is this right here: unmeasured anions minus unmeasured cations. So say you have an organic acid, and that breaks down to A minus plus H plus. Now these protons are going to be quenched by the bicarbonate, so they will not be in the unmeasured cation group. But these anions are going to be in the unmeasured anion group. And for every 1 anion that you get, you have a drop in bicarbonate. It's a 1-to-1 ratio. For every 1 A minus that you generate, you're going to have a proportional drop in your bicarbonate. That's how the delta-delta works. The change in the anion gap is a surrogate or an indirect indication of the amount of protons that have been liberated, because it works on the premise that the amount of protons liberated is proportional to the amount of anions, which is causing your anion gap to change. Those protons should then cause a proportionate drop in bicarbonate. And since we're looking at the changes in all of these, the changes should be the same, and therefore your ratio should be 1. So in a pure anion gap metabolic acidosis, the change in your anion gap divided by the change in your bicarbonate should equal 1. Of course, there are conditions when that's not the case, and let's go through what those conditions are. So again, we go back to our same formula, since this is really the root of how the delta-delta came into existence. Let's look at scenario 1, where you have a delta-delta, which equals a change in the anion gap over the change in the bicarb. So we'll drag this out a little bit. We'll say that the normal anion gap in a patient is 12. This is the current anion gap in their acidotic condition. We'll say that the normal bicarbonate is 24, and that this is their new bicarbonate. And we'll say that that's less than 1. Some fraction, like 0.5 or 0.6, but something less than 1. Now, how does that happen? Well, we said that any organic acid will liberate a proportional amount of anions and protons. These anions will cause the anion gap to change, and these protons will quench the bicarbonate and thereby cause the bicarbonate to change. And actually, I should correct myself. I made a little error here. Forgive me, I wrote this the wrong way. It should be your anion gap minus what's normal, and that's 12. There you go. So again, these anions cause the anion gap to rise. These protons cause the bicarb to fall. The rise and the fall will be proportional to each other. The changes will be proportional to each other, and they should equal 1. When do they equal less than 1? Well, look at this formula. The only way that you can make this fraction less than 1 is if you make the denominator much larger than it ought to be. The only way to make the denominator a larger number is if you make this particular term right here as small as it can be. So you have to have a drop in bicarbonate that's greater than what you'd see if you just liberated an organic acid. In other words, the protons that come from this chemical equation cannot be the only reason why the bicarbonate has dropped. There must be some other mechanism by which bicarbonate has dropped, and that other mechanism is generally a non-anion gap metabolic acidosis. So when you have a delta-delta that is less than 1, you are looking for a non-anion gap metabolic acidosis superimposed upon your anion gap metabolic acidosis. And the reason that is because the change in the bicarb is greater than the change in your anion gap. Something else is driving bicarb down other than the protons that are liberated by this chemical equation. And that's these conditions, like diarrhea, for example. So let's look at the other alternative, which is a delta-delta that's greater than 1. Alright, so that's your anion gap minus what we consider to be normal. And what we consider to be a normal bicarbonate minus what the patient's current bicarbonate is. And now we're saying it's greater than 1. So how can this be? Well, the only way this formula can be greater than 1 is if the denominator is smaller than the numerator. The only way the denominator can be small is if this term, the bicarbonate, is higher than what we expect it to be based on this chemical equation and this chemical equation. So the only way the bicarb can be higher than what we expect is if there is some alkalemic process that's superimposed on your metabolic acidosis process. Something is causing the body to hold on to bicarbonate despite these organic acids quenching bicarbonate in a one-to-one manner. So that's the metabolic alkaloses that are superimposed, like for example being volume depleted. And so we use the delta-delta to determine if there's any superimposition of an acidosis, a non-anion gap acidosis or a metabolic alkalosis on top of a anion gap metabolic acidosis. When you have a delta-delta that's equal to 1, you have a proportional decrease in bicarb. Let me change that here for you. Proportional decrease in bicarb for every increase in protons. Remember, we're measuring bicarb directly. That's here in the denominator. We can't measure protons directly because that's cumbersome, so we're using the fact that every proton liberates a proportional amount of anion. That anion increases the anion gap in a manner equivalent to the drop in bicarbonate, so the ratio is 1. This is a pure anion gap metabolic acidosis. Now, of course, you'll have conditions in the real world where you'll have a ratio that's close to 1, but not exactly 1, 0.8, 1.2, and that's fine. That's probably a pure anion gap metabolic acidosis as well. When you have a delta-delta that is less than 1, you don't have a proportional drop in bicarb for every rise in protons. You have a disproportional drop. More bicarb is lost than can be accounted by the protons that are being generated. And so in these cases, you have a superimposed non-anion gap metabolic acidosis. And finally, if you have a delta-delta that's greater than 1, then you have less bicarbonate loss than protons generated. And so you have a superimposed metabolic alkalosis. And there you have it. The three main ways that you can, three different scenarios, I should say, of the delta-delta that ought to help you identify more complicated acid-base scenarios. I hope this tutorial was helpful, and thank you for watching.